Welcome to the lecture Industrial Ecology as System Science, which is part of the Industrial Ecology Open Online course. In this rather technical lecture, we want to recapitulate the systems approach to studying global sustainability, learn about the concepts socioeconomic metabolism and industrial ecology, and then identify the core industrial ecology system linkages and the related research questions. The general setting is that sustainable development can only be achieved by a very broad array of different development strategies. We not only need technological solutions, we also need lifestyle changes, we need economic incentives, and we need a legal framework that can bind it all together. The question is now how these different strategies can work together to make sure that we are on a path towards sustainability and not on a path away from it, for example, due to rebound effects. The different ecosystems and technical systems on the globe are interconnected. For example, soy farming in Brazil is part of the meat supply chain of China. This supply chain leads to carbon emissions, which leads to global warming, which for example leads to that an increased amount of dust is taken up in the Sahara Desert and deposited in the Caribbean Sea. So you can see that there's intricate linkages between the different systems and the elements of the system on this planet, and we need a systems approach to study these linkages to see which ones are relevant, which ones we can impact, and which ones are maybe not so strong. To do that, we need a systematic approach to the whole problem, and this approach is called socio-ecological systems. So we study systems that have both biophysical and social factors, meaning that we have ecosystems, that we have industries, and natural resources. So these are the biophysical aspects where the laws of physics and chemistry apply, but we also have social elements in the systems. We have human values, we have economics incentives, we have legal institutions. And these two layers, the biophysical layer and the social layers, they are truly interlinked and interdependent. For example, we cannot understand our society, how it works, if we don't consider the physical layer, the combustion of fuels, our own metabolism, and all the waste generation, for example. At the same time, many of our physical processes in society are non-comprehensible without the legal and economics incentives behind it, for example, all the consumption that we do. The socio-ecological systems is a complex, adaptive, and a self-reproducing system, meaning that it has many non-linear effects, it can adapt to changing environmental conditions, and it can reproduce itself, meaning that the society itself brings forth the institutions and the new industries, the new products that then create the basis for the living of the next generation. This is self-reproduction over time. There's other terms, there's the human environment systems, and there's the coupled human and natural systems. And these, at least for the purposes of this lecture, can be roughly seen as synonyms to socio-ecological systems. Systems theory here is a kind of complementary sciences. It complements the natural and the social sciences. That means we can take the laws of sciences, the physical laws, and the laws of economics, for example, and integrate them here in the common system that can be studied. The reason is that the sustainability challenge is so complex that there is no scientific field that can study all relevant facets of it. We need different fields to come together and identify which are the important system linkages in the socio-ecological systems. For example, the physical and monetary stock flow relations are important to study, or the life cycle perspective, or behavioral and societal change. So we have, with the systems approach, a basis on which the different fields, economics, physics, engineering, can come together and study the system, study sustainability from an interdisciplinary perspective. We can conceptualize the socio-ecological systems as follows. We said there's two layers or two spheres of causation. There is a biophysical reality where we can understand how industrial processes work or how our own bodies work. And there's the social reality where we can understand how our values are linked to consumption decisions, or how ownership is linked to what is produced in which quantities. And the interesting part is where both realities overlap. So where we have both a physical reality and a social reality. And this is, so to say, the core of our society. These are biophysical structures like consumption processes, supply chains that are governed by social actors. So these two layers, biophysical and social, are the two layers of the socio-ecological system. Within this overlap, the overlap between the biophysical sphere and the social sphere, we have a threshold of control. We have processes that we fully control, for example, what's happening in the steel industry or what's happening inside the engine of a car. But there's processes that have a social component and a natural component, but that are not much under our control. For example, forests, which we manage a little bit, but where the trees grow how they want to grow, and where also biodiversity can thrive according to the environmental conditions. So there's different levels of control that we have over the world around us. And the part of the system that it's completely under our control, this is the biophysical basis of our society. These are the processes and the products and the structures we need and operate to maintain our society. The supply chains, our houses, the vehicles we own, the products we consume and use. And this biophysical basis of our society has, again, two layers. The first one is the structures. Structures are the things that are there, the things that are controlled by us. The vehicles, the infrastructure, the products. And with this structure, we want to have service generation. We want to create services like thermal comfort or transportation, and we need to operate the structures to get those services. For example, we need to drive the vehicles. And this operation of the structures is called the metabolism of society's biophysical basis or socioeconomic metabolism. Typical structures are shown here. Again, it's our own bodies, the muscles, the bones that hold us together. They are one aspect of the basis of our bodies. And then there's the physical basis of our society, the buildings, the infrastructure. It's the stocks that we have or the structures. Typically, this is what you see on the picture when you photograph a technical systems. So these structures provide services to us. And when we operate the structures, when we, for example, ingest nutrients and water, our organs begin to work or they keep working. The same applies to buildings and vehicles. When we put in gasoline and we hit the gas pedal, the vehicle starts driving, and so it provides the service while transforming energy and material into other products. And this transformation, this operation of the biophysical structures, this is the metabolism of our society. This is all energy and material input and output and all technical transformation that happen to build up and maintain the structure of our society. That means we can say socioeconomic metabolism constitutes the self-reproduction and evolution of the structures of our society. It's all the transformation processes, the stocks and the flows that are controlled by humans for their purposes. And when we take together the metabolism, which are the throughput, the flows, and the structures, which are the stocks, they both together form the biophysical basis of society. Socioeconomic metabolism is a way of framing the system, of looking at it. It's a scientific principle. We want to study human nature interactions from a systems perspective. And the science that does that is called industrial ecology. Industrial ecology is the interdisciplinary science for studying sustainable development. It is the study of stocks and flows of materials and energy in industrial and consumer activities, of the effects of these flows and environment, and of the influences of economic, political, regulatory, and social factors on the flow, use, and transformation of resources. This is the common definition of industrial ecology. We can say it also shorter, but more technically, industrial ecology is the science that studies socioeconomic metabolism. The science that studies how the physical structures of a society change and how the metabolism changes. The core elements that industrial ecologists study are shown here. We again start with the two-sphere model of society and the biophysical sphere of causation and the control threshold that divides the biophysical world into the natural environment on the left side of the control threshold and into the technosphere or anthroposphere on the right side. And in that anthroposphere we have households, we have industries, and we have markets that distribute products to households and other industries. This is the industrial metabolism or the socio-economic metabolism. Then we have emissions to nature, we have resource uptake, and on the natural environment side we have the environmental mechanisms like ocean acidification or global warming that link our impacts on the natural environment to, for example, effects like damage, like biodiversity loss. So these elements are studied, and we want to now see how the different parts of the systems, the industry or the consumptions, are studied by the different subfields of industrial ecology. In particular, industrial ecologists focus on specific system linkages in the global socio-ecological system. The global SES is a complex system. There's many actors, there's many causal loops, there's economic effects, there's physical effects, many things to study, and as we said before, no discipline can do it all. What a discipline can do, it can select certain linkages in the systems that it has identified as important and can study those from a scientific perspective and offer the insights to other disciplines and to the broader societal discourse. This is exactly what industrial ecology does as well. This slide lists the core system linkages studied by industrial ecology. It's global supply chains, it's the linkage between service provision, capital stocks, and energy flows, it's material cycles, it is the importance of co- and byproduct generation and waste generation and use, and is the so-called urban fabric and the link to consumption patterns. There's different methods that we apply our field. There's life cycle assessment, material flow analysis, and so on. We will have a method lecture later. And the different methods focus on specific system linkages that are at the core of their working. And they study those system linkages applying different principles like the mass balance, high level of detail, or vintage tracking. So industrial ecology has a set of methods that study different system linkages applying different modeling principles. A prominent linkage is global supply chain. A typical research question here is to quantify how much of a certain substance is emitted in the global supply chain of a certain product. For example, greenhouse gases in the supply chain of electric vehicles. This question is studied by looking at the system linkage of global supply chains. It's also called telecoupling. We want to connect remote resource extraction and material production to consumption that happens here in front of our eyes. And the methods we apply here is life cycle assessment and also environmental extended input-output analysis and also combinations thereof, so-called hybrid models. So this is the first core system linkage, global supply chain. We also study the service capital stock flow linkage. A typical research question here is how big are the material and energy flows that are needed to expand and operate the service providing stocks. For example, what is the resource requirement of the energy transition? How much steel and aluminium do we need to build all the wind turbines and the solar panels to then generate electricity that has a low carbon footprint? And also here life cycle assessment is an important method because it can link the different material and energy flows to the service unit provided. But also material flow analysis and urban metabolism studies are important. The third linkages is material cycle. Typical question here is, how big are the societal stocks and flow of a certain material that provide a certain service? For example, how large are the steel stocks in residential buildings, and also how much can we recycle from torn down residential buildings in the future? Material cycles are, of course, studies using material flow analysis, but also life cycle assessment can have an important say here, especially when we want to link material cycles to energy consumption and environmental impacts. Co-production and waste utilizations are core industrial ecology concepts. Actually, the whole notion of industrial ecology stems from the idea that one industry's waste should be another industry's raw material. So we can ask ourselves, how big are the resource and emission saving when using waste as a feedstock for industrial production? These are typical questions that are studied when we look at co-production and waste utilization. Basically, all industrial ecology methods are fit for doing that, so we can apply life cycle assessment here, material flow analysis, but also environmentally extended input-output analysis. And finally, industrial ecologists study the linkage between urban fabric and consumption patterns. For example, we want to know how big are the energy and material requirements of cities depending on the city pattern. How can cities transform themselves to become less unsustainable? Where do we need to locate industry? Where do we need to locate residential and recreational areas so that certain transport patterns emerge that, for example, are easier to be satisfied with public transport? We have now had a look at the 5 core industrial ecology system linkages. Here is now a quick overview of the history of the concept industrial ecology. Many of our colleagues date the field back to an essay from 1968 called The Cowboy versus the Spaceman Economy, where the author, Kenneth Boulding, explains how an ever-growing economy is in conflict with the biophysical limits of the planet, and he proposes the idea of a spaceman economy where there is basically no waste because all waste flows are somehow recycled or at least dealt with in a way that they are not harmful to the environment. Also in the 60s, the general systems theory emerged. And the systems theory is the scientific underpinning of the entire field. It motivates why we can study telecoupling, for example, remote supply chains, or why we can do dynamic modeling linking today's consumptions to future service provision. For example, when we build a building today that can provide service for many decades. In the late 80s, there was a piece in Scientific American called Waste from one industrial process can serve as a raw material for another. Again, lining out the vision of an industrial ecology or industrial ecosystems, as the process was then called, with the idea that we can implement the so-called industrial symbiosis in the system, meaning that systems, industrial processes together can thrive by reusing each other's waste flow. In 1997, we had the Journal of Industrial Ecology founded, which is still today the main journal of the community, in particular when it comes to publication of forum and discussion pieces and also methodological advances. In 2001, the International Society for Industrial Ecology was established, in short ISIE. Since 2000, several master's and PhD programs for industrial ecology have been set up. And it is interesting to see that the label industrial ecology is thriving differently in different countries, mainly because it's a US-based label, but the methods that are now comprised under that label origin from different regions. Most of them were developed in Europe, for example, material flow analysis and also parts of life cycle assessment. So we have now a label, industrial ecology, that rings a bell for some people but doesn't so much ring a bell for other people. But it's important that we have this label because it really can help us to understand that these different methods that we use on a daily basis actually work together and are part of describing the larger system, which is the socio-economic metabolism. Industrial ecology is closely related to other fields, for example to social ecology. In social ecology, we also study the coevolution of society and its natural environment from an interdisciplinary perspective. The difference is that in industrial ecology there's more detailed focus on the industrial system and specific processes, whereas social ecology studies the biophysical flows from a more aggregate perspective, but always in connection to social practices. For example, what's shown here to the different human development stages. Industrial ecology is also linked to energy systems modeling and integrated assessment modeling. Again, the main difference here is that industrial ecology is a very detailed science. Very specific technologies and products are studied, but then again, when you study so specific systems, it's very hard to make meaningful scenarios because so much around your detailed foreground system can change. This is the advantage of integrated assessment models. They have, let's say, big picture, long-term scenarios of how the industrial ecosystem can be transformed, for example, by switching to renewable energies. And of course, there's good synergies and interesting research questions when we combine the two. For example, by coupling industrial ecology science life cycle assessment with integrated assessment models, you can find out how the greenhouse gas emissions of photovoltaics that will be produced and operated in the future will change compared to what the carbon footprint of photovoltaic electricity is today. Industrial ecology is also very closely linked to chemical engineering, and there's a saying by Roland Cliff that industrial ecology is chemical engineering beyond the pipe. Both fields apply mass and energy balances and the second law of thermodynamics and make frequent use of linear process models and optimization. The difference is that industrial ecology is, I would say, a bit more big picture, so we also study material flows and we lift chemical engineering to the society as a whole. So we are not studying individual chemical plants, we study networks of chemical plants and of networks including industry, end users and waste management. So the same principle as in chemical engineering, but the system level is 1 or 2 steps up. There's a link to ecological economics, where we can say that ecological economics are a broader discipline and have less technical focus than industrial ecology, and they have also a more conceptual focus. Whereas industrial ecology is more close to engineering and there's more modeling and quantitative assessment. And that again means there's a lot of good opportunities for linkages, for example, making meaningful scenarios for sufficiency and other sustainable development strategies. Finally, we can say that industrial ecology is part of the broad sustainability science. It's a biophysical and engineering approach to analysis of socio-ecological systems, which is complementary to the many other approaches that we need to actually meaningfully describe and scientifically describe the process of sustainable development. So industrial ecology has a lot to offer, but to really have decision-relevant information, it needs to be linked with the insights of other disciplines. We offer knowledge on the 5 core system linkages that we study, and again, we can offer insights on those system linkages to other stakeholders, policymakers, other scientists, and the general public to understand how the industrial system works and what the constraints and opportunities are for its sustainable transformation. Thank you for your attention.